everyone. Today we're going to wrap up Module 5 and we're going to discuss something called limiting reactant, and then we'll also talk about percent yield. So in any chemical reaction, if you have two or more reactants, one of those reactants is going to run out first in a typical chemical reaction. So this is very similar to if you're baking. Let's say you're trying to make a cake and you need some flour, some sugar, some eggs, etc., but you only have 2 eggs. So those 2 eggs are going to limit how much cake you can make. And that's the same for a chemical reaction. Now, in a different example here, let's say we're making a peanut butter sandwich. And you need 2 slices of bread, so that's one of our reactants. And then you also need a tablespoon of peanut butter, so that's our other reactant. So we could write this as a chemical equation. So you need 2 slices of bread plus 1 tablespoon of peanut butter, and that will make 1 sandwich. All right, so you have a 2 to 1 to 1 ratio there. Now, let's say you rummage around in your cabinet and you find, oh, I have a whole loaf of bread. Cool. Oh, but I only have a tablespoon of peanut butter left. So maybe you forgot to pick up peanut butter at the store. That means that the peanut butter is going to run out first. So that's going to limit the amount of sandwiches you can make. So in that example, you can only make 1 sandwich. So you have a bunch of bread, but you only have 1 tablespoon of peanut butter. So that means that the limiting reactant is your peanut butter, and the excess reactant is the bread. So you'll have a lot of leftover bread. Now, what if you're rummaging around in your pantry or your cabinets and you find that you only have 4 slices of bread, but you have a full jar of peanut butter? Now, in this case, you're going to run out of bread first. And we know that we need 2 slices of bread for every sandwich. So that means you can only make 2 sandwiches. So in this example, the limiting reactant would be the bread, and the excess reactant is the peanut butter. All right, so chemistry is exactly the same, except instead of making something you can eat, we're making chemicals. We're making new compounds, new substances. And depending on how much of each reactant you have, one of the reactants could run out first and limit the amount of product you can make. So a limiting reactant in a chemical reaction is the substance that is used up first. So it limits the amount of product that can form. Now, the reactant that does not completely react and is left over at the end of the reaction is called the excess reactant. So for instance, on the previous slide, we saw that if you have a full loaf of bread, but only 1 tablespoon of peanut butter, we'll have a lot of excess bread. So that was our excess reactant. All right. So again, in many reactions, there is a limiting reactant that determines the amount of product that can be formed. So given a chemical reaction, we can look at each reactant individually and see how much of each we have. And from each of those reactants, we can calculate the amount of product that is possible. So the theoretical yield. So that's theoretically how much we could form when that reactant is completely consumed. And then we can determine from that calculation which reactant will run out first. So which one is the limiting reactant? So the limiting reactant is going to produce the smaller amount of product. So as an example, let's think about our peanut butter sandwich example. So let's say we have a full loaf of bread. So let's say that's 20 slices of bread. Well, we know that we need, for every one sandwich, 2 slices of bread. Okay, so let's say we used all 20 of those slices of bread. We could make 10 sandwiches. Okay, now in that same example, I think we only had 1 tablespoon of peanut butter. And in our quote unquote chemical reaction, for every 1 sandwich, we need 1 tablespoon of peanut butter. Okay, so that means we can only make 1 sandwich with that amount of peanut butter. All right, so comparing the two reactants and how much product can form, we can see that we're limited by the peanut butter, right? So we can only make 1 sandwich overall. So that is our theoretical yield. So even though we have enough bread to make 10 sandwiches, we're limited by the amount of peanut butter, which is only 1 tablespoon. So that peanut butter is our limiting reactant, which means we can only make 1 sandwich. So we're going to apply this same idea to chemical reactions. We're going to look at each reactant individually. We're going to calculate how much product each reactant could make if we used all of each reactant. And then we're going to compare the amount of product that can be made from each reactant. So for instance, in this example, we're comparing the 10 sandwiches to the 1 sandwich. And that's going to tell us which reactant runs out first, and that will be our limiting reactant. Okay. So let's start out with an easy problem, and then we'll kind of work up to a more difficult problem. So let's say we're performing a reaction between carbon monoxide and hydrogen gas. And let's say we start with 3 moles of carbon monoxide and 5 moles of hydrogen gas. And we want to figure out how many moles of the product can be produced and what is the limiting reactant. So which reactant will run out first? Okay, so down below we have our balanced equation. We have 1 mole of carbon monoxide reacting with 2 moles of hydrogen to produce 1 mole of methanol. And remember, methanol is the alcohol you do not want to drink. That can have terrible consequences. All right, so let's figure out what is our limiting reactant. So what we're going to do is calculate how much product can form from each of our reactants. Okay, so we're given that we have 3 moles of carbon monoxide to start and 5 moles of hydrogen to start. So we're going to convert each of these to moles of the product. And then we're going to compare those amounts and figure out which one is smaller. And whichever one is smaller will tell us which reactant is limiting in this instance. Okay, so let me erase this and we'll actually do that conversion. All right. right, so we're just going to use molar ratios for this problem. So we'll set up both of these here. Okay, so let's look at our first conversion factor for carbon monoxide. We want to figure out how many moles of methanol we're going to form if all of the carbon monoxide reacts. Okay, so we're going to try to cancel moles of carbon monoxide. So looking at our balanced chemical equation, what is the ratio between methanol and carbon monoxide? It's just 1 to 1, right? So we have invisible ones in front of carbon monoxide and methanol. So this would be 1 to 1. All right. Okay, so what that tells us is if we completely react all of the carbon monoxide, we'll end up with 3 moles of methanol. Okay. Now let's do the same for hydrogen. So again, we want to end up with moles of methanol. Oh, not moles of CO. We want moles of hydrogen to cancel. Okay. So what is the ratio between methanol and hydrogen in our balanced equation? 1 to 2. All right. So we'll cancel out moles of hydrogen, and 5 divided by 2 is 2.5. All right, so now we're going to compare those two amounts of methanol. So whichever one is smaller will tell us the limiting reactant. Okay, so 2.5 is smaller. So that tells us that hydrogen is the limiting reactant. It's going to run out first. And 2.5 moles is the largest amount of methanol that we can potentially make because hydrogen is going to run out. So once hydrogen runs out, we can't make any more methanol because we need both reactants to make methanol. So 2.5 moles will be our theoretical yield. So theoretically, we can make 2.5 moles of methanol. All right. Now, there is another way to solve this problem. So if you have taken chemistry before, maybe you saw a different method. So for instance, another way to figure this out is to compare the reactants to each other. So for instance, carbon monoxide and hydrogen react in a 1 to 2 ratio. So if we start with 3 moles of carbon monoxide, we would need 6 moles of hydrogen. So if we start with 3, we need 6 moles of hydrogen. So we only have 5 moles of hydrogen, which means hydrogen will run out first. So that's another way to think about it. You could compare the reactants together and kind of figure out which one is limiting or which one runs out first. So that's another option. Whatever works for you or however you like to think about it, as long as you show your work and demonstrate that you understand the process of figuring out which reactant is limiting. I've seen it all, so I can definitely interpret your work. Okay, so in this problem we only focused on moles, but oftentimes we're given amounts in grams. So we might need our entire flow chart that we saw in the last video. All right, so again, quantities of reactants can also be given in grams. So in this instance, to figure out the limiting reactant, you're going to first convert the grams of each reactant to moles of that reactant using molar mass. Second, you're going to use mole-to-mole factors to convert moles of reactant to moles of product. And then third, you're going to use molar mass to convert the moles of product to grams of product. And then whichever reactant produces the least amount of product is the limiting reactant. So that, again, this is just our flow chart that we saw last time. So mass of A is converted to moles of A, and then we convert that to moles of B, and then we convert that to mass of B. But this time we're going to do that for each reactant. And then we'll compare the answers and see which reactant produces the least amount of product. Okay. So let's go over a problem together. In this problem, we have silicon carbide, SiC, and this is a ceramic material that tolerates extreme temperatures. So it's often used as an abrasive and also in the brake discs of sports cars. So down below is the reaction to produce silicon carbide. So you need silicon dioxide and carbon, and then you react those together to make silicon carbide and carbon monoxide. So let's say we're trying to figure out how many grams of carbon monoxide are formed from 70 grams of silicon dioxide and 50 grams of carbon. Okay, so we're given that we start with 70 grams of silicon dioxide and 50 grams of carbon. And we want to figure out how many grams of carbon monoxide is formed. All right, so maybe we're trying to figure out, how much of the byproduct is formed. Okay, so let's write out our plan for this problem. All right, so we're going to use the mass of each reactant and then convert each of those to moles. So we're going to need the molar mass of silicon dioxide as well as the molar mass of carbon. And then in the next step for each process, we're going to figure out the moles of the product. So carbon monoxide. And so for that, we'll need the molar ratios. So we'll just get that from the balanced equation up above. And then finally, in the last step for each process, we're going to figure out the mass of carbon monoxide. So we'll need the molar mass of carbon monoxide. Okay, so these are our two flowcharts, and then at the very end, we'll compare the masses of carbon monoxide, and whichever one is smaller will tell us what reactant is our limiting reactant. Okay, so I'm going to erase these flowcharts, and we're going to calculate the molar masses of silicon dioxide, carbon, and carbon monoxide, because those are what we need for our problem. Oh, I'll just clear the pen markings. Okay. Oh, so let's start by calculating the molar mass of SiO2. All right, so you might need your periodic table for this part. So the mass of silicon is 28.085. All right, and then we only have 1 mole of that, but we do have 2 moles of oxygen, so 2 times 16. Okay, so I'm going to plug that into my calculator. All All right, so the mass that I get is 60.09 grams per mole. All right. Now the next molar mass we need is the molar mass of carbon. And that one's super easy. We're just going to look on the periodic table. So the mass listed under carbon is 12.01 grams per mole. Cool. Okay, so that didn't need much work. And last, we're going to calculate the molar mass of carbon monoxide. Okay, so we need the mass of carbon, which is 12.01, and the mass of oxygen, which is 16. Okay, so if we add those two together, we get 28.01 grams per mole. Okay, so those are the three masses that we're going to use in our calculations. All right, so let's go through our flow charts. Oh, if it will let me. Let's see. Oh, I might have to back out. Oh, technical difficulties. All right, there we go. Okay, so let's start with our first flow chart. All right, so we're going to start with the mass of silicon dioxide. So that was 70.0 grams. And we're going to convert that to moles of silicon dioxide. So remember, we just calculated that 1 mole of SiO2 is equal to 60.09 grams of SiO2. All right. So as we've seen previously, we want to convert to moles in this step. So we're going to put 1 mole of SiO2 in the numerator, and we're going to put the mass in the denominator. Then in the next step, we need to compare the ratio of the product to our reactant. So looking at our balanced equation, we have 2 moles of carbon monoxide and 1 mole of silicon dioxide. So we're going to put 2 moles of carbon monoxide in the numerator because that's what we're trying to calculate. And we're going to divide that by 1 mole of SiO2. And then in the last step, we're going to convert to grams of carbon monoxide. All right, so remember 1 mole of carbon monoxide was equal to 28.01 grams of carbon monoxide. And we want grams, so we're going to put that in the numerator, and we're going to cancel moles of carbon monoxide. All right, so let's make sure all of our units cancel. So grams of silicon dioxide cancels with grams. Moles of SiO2 cancels with moles. Moles of carbon monoxide cancels with moles of carbon monoxide. Perfect. So our final unit is grams of carbon monoxide, which is what we want. All right, so let's simplify our math here. So in the numerators, we have 70 times 1 times 2 times 28.01. And in the denominators, we have 60.09 times 1, so I'll just leave those out. And then our final unit is grams of carbon monoxide. Okay, so let's plug that into our calculators and figure out how many grams of carbon monoxide could be produced if all of the silicon dioxide reacts. So 70 times 2 times 28.01 divided by 60.09. We get 65.23548, etc. But how many sig figs should our answer have? So looking at our numbers here, it looks like our first value has 3 sig figs because both of those zeros are significant. Let's see, in our second conversion factor, we have an exact value, 1 mole, and then 4 sig figs for our mass. In the second conversion factor, we have 2 exact values. And in our final conversion factor, we have 4 sig figs over an exact number. All right, so we need 3 sig figs in our final answer. Okay, now the first digit we're dropping is a 3, so we don't have to round up. So this will just be 65.2 grams of carbon monoxide. All right, so we still have to do this for our other reactant, carbon, and then we'll compare the answers to each other. So we'll come back to this. All right. So for this flow chart, we're starting with 50 grams of carbon. And we're just going to do the same thing we did before, but we're going to use the molar mass of carbon and then the molar ratio between carbon and the product. Okay, so starting with the molar mass, 1 mole of carbon is equal to 12.01 grams of carbon. And then in the second conversion factor, we need the mole ratio. So looking at our balanced equation, we have 2 moles of carbon monoxide for every 3 moles of carbon. Okay, and we want to end up with moles of carbon monoxide. So I'm going to put that in the numerator. And we'll divide by moles of carbon. So there are 3 moles of carbon. Okay, and then in the last step, we're going to convert to grams of carbon monoxide. So we're just going to use that same molar mass that we calculated earlier. All right, now let's make sure that everything cancels that we need to cancel. So grams of carbon, moles of carbon, moles of carbon monoxide. So our final unit again is grams of carbon monoxide. Okay, so let's simplify this. So in the numerators, we have 50 times 1 times 2 times 28.01. And in the denominators, we have 12.01 times 3 times 1. Okay, so let's figure out how many grams of carbon monoxide will form if all of the carbon reacts. So 50 times 2 times 28.01 divided by, and remember to put parentheses around your denominator there. All right, so I get 77.74, etc. But how many sig figs should we have? 3. So this is similar to before. So we need 3 sig figs. So we'll limit this to 77.7 grams of carbon monoxide. Okay, so now we're going to compare that value to our previous value. All right, so previously we saw that silicon dioxide, if it all reacts, will produce 65.2 grams of carbon monoxide. So let's write that down. Oh, did I write that correctly? Yes, okay, great. And then carbon, if it all reacts, will produce 77.7 grams of carbon monoxide. Okay, so comparing those two values, which one is smaller? 65.2. All right, so that tells us that silicon dioxide is our limiting reactant, which I'll abbreviate LR. What this also tells us is that we can only form 65.2 grams of carbon monoxide because silicon dioxide is going to run out at that point. Okay, so even though we started out with a lot more silicon dioxide compared to carbon, silicon dioxide does run out first. And that has to do with the ratios in our chemical equation, but also the masses of each. So you do have to go through that flow chart in order to figure out what is your limiting reactant. Because initially, looking at the amounts of each reactant, 70 compared to 50, I would assume carbon would run out first, right? But that's not the case when we actually calculate it out. It's actually silicon dioxide that runs out first. So you do have to go through that whole process to figure this out. Okay, so hopefully that helped a little bit with understanding limiting reactants and also how to determine which reactant is limiting. And here are the solution slides if you want to go over those later. Oh, I think there's a typo here though. That should say carbon, not H2. All right, and then we got the same answers and we got the same limiting reactant, SiO2. Awesome. Okay, so now let's talk about percent yield. So often in chemistry, reactions don't happen perfectly. Maybe you weighed out a certain amount of reactant, but then spilled some on your way to the beaker or something. Or maybe you didn't provide enough heat for the reaction to complete. So when a reaction does not go to completion, or if some of the reactant or product is lost, then the actual amount of product that you produce might be less than what you would assume or what you would calculate. So this is kind of similar to, let's say you're making pizzas and you plan on making 5 pizzas for a party. And this is obviously during a non-pandemic time. And then let's say, you're taking the pizzas out of the oven and one of them drops on the floor. Well, now you only have 4 pizzas. So you actually made 4 pizzas out of the total 5 you were expecting to make. And that's the same with chemistry. Stuff can go wrong, errors can occur, so you might not actually make the full amount of product that you expect. So we have a few different terms here. So theoretical yield, we kind of already went over. This is the maximum amount of product that you could make based on your calculations. And then the actual yield is the amount of product you actually make. And then your percent yield is the ratio of your actual yield to the theoretical yield. So that's shown down below. So percent yield is equal to your actual yield, so what you actually made, over the theoretical yield or your calculated amount. And then we just multiply that ratio by 100 to get our percent. Now in chemistry, you might be surprised, chemists are often happy with really low percent yields depending on the reaction they're performing. So a lot of chemistry involves coming up with more efficient ways to make a product or better ways to make a product. So for instance, in some reactions, you might only have a 20% yield. And that sounds awful, but in certain reactions, that's the best you can expect. Some reactions are super efficient, super effective, and you end up with like a 90% yield. It just kind of depends. Um, so let's do a practice problem with percent yield. On a space shuttle, lithium hydroxide is used to absorb exhaled carbon monoxide from breathing air to form lithium bicarbonate or lithium hydrogen carbonate. What is the percent yield if the reaction, of the reaction, if 50 grams of lithium hydroxide gives 72.8 grams of lithium bicarbonate? And down below we have our balanced equation between lithium hydroxide and carbon dioxide. So they react in a 1-to-1 ratio, and they produce 1 mole of lithium bicarbonate. Okay, so what we're given in this problem is a starting amount of lithium hydroxide. And then we're told that that actually produces 72.8 grams of the product. So this is our actual yield. So let's write that down here. Actual yield is equal to 72.8 grams of our product. So we need to determine the percent yield. Now remember, percent yield is equal to the actual yield over the theoretical yield times 100. So we were told the actual yield, but we don't know what the theoretical yield is. So that's a question mark. So in this problem, what we're really trying to figure out is what is the theoretical yield, because then we can calculate the actual yield. Okay, so what we need to do is figure out if all 50 grams of our lithium hydroxide reacts, how much product could theoretically form? Now, we're not told anything about carbon dioxide. We're going to assume that carbon dioxide is in excess. So there's just plenty of carbon dioxide in the air. So that will be our excess reactant, which means that we already know lithium hydroxide is our limiting reactant. So we're just going to focus on lithium hydroxide and just ignore CO2. All right, so let's go through our flow chart that we've gone through before. Okay, so we're starting with 50 grams of lithium hydroxide. And then our first step, we have to convert to moles, which means we need the molar mass of lithium hydroxide. So let's figure that out down below. Okay, so the molar mass of lithium hydroxide. So we have 1 lithium, and that has a mass of 6.94 grams per mole, looking at our periodic table. And then we're going to add that to the mass of our 1 oxygen, which is 16. And we'll add the mass of our 1 hydrogen. Oh, grams per mole. Just imagine a grams per mole over there. Okay, so let's plug this in. I get 23.95 grams per mole for lithium hydroxide. All right, so we'll put the 1 mole of lithium hydroxide in the numerator, and we'll put the mass in the denominator. All right. Now in the next step, remember we're going to use molar ratios to convert from moles of our reactant to moles of product. Now, luckily, everything's in a 1-to-1 ratio. So we'll just put 1 mole of our product over 1 mole of our reactant. Okay, easy enough. And then in the next step, we need the molar mass of our product because we want to figure out how much of our product is formed. So let's calculate the molar mass of our product. Okay, so there's a few more atoms in this one. Let's see, we still have 1 lithium, so that's 6.94. I'm just going to leave out the units and add together all the masses. So hydrogen is 1.008, carbon has a mass of 12.01, and then we have 3 oxygens, so 3 times 16. Okay, I'm being a little sloppy with my decimals there. All right, so 6.94 plus 1.008 plus 12.01 plus 3 times 16, which is 48. So I get 67.96 grams per mole for lithium bicarbonate. And remember, we're going to put the mass in the numerator so that we end up with grams of our product. Oh, I'll squeeze in the name there. I ran out of room. And then 1 mole of lithium bicarbonate. Okay, so let's make sure our units cancel. So grams of lithium hydroxide cancel, moles of lithium hydroxide cancel, and moles of lithium bicarbonate cancel. Awesome. That's exactly what we want because we want to end up with grams of our product. All right, so let's make some room down here. And we're going to simplify our math. So we have in the numerator 50 times 67.96. And then in the denominator, we have 23.95 times 1 times 1. We'll just leave out the ones. All right, so let's see what our theoretical yield is if all of the lithium hydroxide reacts perfectly. Okay, so 50 times 67.96 divided by 23.95. All right, so I get an answer of 141.8789, etc. And how many sig figs should our answer have? 3, right? So we have our first 3 digits there. So the first digit we're dropping is an 8. So we'll round up to 142. Okay. So this is our theoretical yield. So now we have everything we need in order to calculate the percent yield. So let's do that. Okay, so again, the percent yield is equal to the actual yield over the theoretical yield times 100. All right, so previously we saw that our actual yield was 72.8 grams. And we're going to divide that by what we just calculated, which was 142 grams. And then we'll multiply by 100. All right, so 72.8 divided by 142 is 0.5126, etc. But let's multiply that by 100, and we get 51 point, I'm going to round it, 3%. Okay, So that means that there's, something going on here where we're not getting 100% of the yield we expect. We only get about 50% of the yield. But again, in some chemical reactions, that's okay. That's, just how it goes. All right, so hopefully this helps a little bit with understanding theoretical versus actual yields. How do we calculate an a theoretical yield? And then what is a percent yield? So percent yields, again, just tell us how much of the product was actually formed. And here are the solution slides if you want to go over that later. And there are a couple of worksheets on Canvas that you can go through to get some extra practice with converting from moles to mass. And then there's one on limiting reactants and percent yield. So you'll get some practice with those flow charts that we went over, and also get some practice applying that to a percent yield. Now, this is also going to relate to the lab that we're doing this week. So make sure you understand this material. And if you do have any questions, just ask. Make sure to email me or contact the Writing and Tutoring Center. They are also extremely helpful. And I will see you next week and we'll start Module 6.